Okay, thank you, Dee. And I'd like to first thank everyone for coming, and also especially thank the organizers of the program and the workshop for inviting me to give this talk. And Dee already explained what the title stands for. This is called PDO or CIDO. This stands for pseudo differential operator. Okay. So, I'm a numerical analyst by training, so I've been spending most of my time working on problems related to PDEs. I mean, under the influence of my colleagues and especially Ling here, so we started working with the algorithm in quantum computing roughly about a year and maybe 2 years ago. So I guess here many people are experts in quantum computing. You know this field much better than I do. Well, from a numerical analysis perspective, one thing I feel very important is that this is a field where you see a lot of things happening. And what I mean is that you see new developments in hardware, you see new developments in algorithms, and also they certainly need new developments in analysis. So this is where we as a numerical analyst can come in. So one important thing is that quantum hardware is very noisy. You have the spam noise, and the device itself can also be quite noisy. So therefore, the algorithm design should really take care of, try to take all these things into consideration. So for example, first the algorithm has to be efficient because the resources are very limited and also noisy. And also, the algorithm itself should try to take care of the noise and errors as much as possible in order to produce meaningful result. So this resembles quite a bit about what the situation for numerical analysis maybe 50, 60 years ago, right? People developed these fundamental building blocks as, for example, approximation, interpolation, and quadrature. And later on, you have numerical linear algebra and numerical methods for solving PDEs and ODEs, and also Monte Carlo sampling. So all these techniques, at different stages of the development of these techniques, you see that people put different emphasis on different aspects of this. So maybe initially there was a lot of discussion on error analysis, backward error analysis. But if you take a look at the recent developments of the classical numerical analysis, which is very much influenced by parallel computer architecture and also deep learning, like the NVIDIA graphics chips, a lot of emphasis has been put on parallelization and vectorization, and how do you leverage the parallelism in the hardware architecture. So this is what's happening, what has happened, but it's still happening in classical numerical analysis. But the same picture is also happening in quantum as well. We have these fundamental building blocks like phase estimation, quantum Fourier transform, and the recent developments on quantum equivalent transformation and also quantum singular value transformation. And probably the oldest field is Hamiltonian simulation. All these things are fundamental building blocks to the bigger field of quantum scientific computing, and how to design efficient algorithm and try to analyze them carefully I think it's a very important new field. It's called quantum numerical analysis. I think the new people sitting here, especially the ones come from applied math community, can do quite a bit in here. Okay. Now, so in this talk, I would like to share with you the two pieces of work that has been done with me and my students. So I forgot to mention all these work are done with my students, Haoya Li and Yihong Kang, who are both here. So they know these content much better than I do. So if you're interested and more about the details, please feel free to talk to them. Okay. So the two parts I'm going to talk about, the first part is called quantum pseudo-differential operators. So here what we want to do is that we want to study one kind of object called a pseudo-differential operator and try to understand how do you actually represent it efficiently on quantum devices and how to work with them. The goal that we're trying to lead into is to try to have very explicit constructions for these differential operators. So we try not to use oracles as much as possible. We're not to use these position and amplitude oracles. We just try to build everything on concrete circuits. And the second part is more about, the first part is more about new algorithms and new constructions. The second part is more about careful analysis. So we're going to come back and revisit quantum phase estimation, which is, you hear about it quite a lot. And here what we want to show is that we want to revisit some old algorithm and also develop a new algorithm and show that they reach Heisenberg limit, and also they can be quite error tolerant. Okay, so that's the plan for this rest of the talk. Okay, so the first part is this I call the acronym is QCIDO. Now, first I have to tell you what is the pseudo-differential operators. So for those of you who come from the applied math community and PD community, you know this quite well. So pseudo-differential operators defined as the following is an operator map from function to functions, and essentially it's written in this form. It's So first you take the input function f. What you do is that you do a Fourier transform it, and then you multiply this with something called a symbol, ax c. This is the function not only of one variable x, but also the dual variable, the Fourier frequency variable c. So once you have done that, you multiply with this phase e to the 2 pi I x c. This is a function of both x and c, and you have seen it many times, for example, in Fourier transform. And at the end, you integrate it over c, and that gives you the result. Okay. Now we need to impose some kind of condition on this symbol here, because otherwise this operator is too general. So the typical condition that people impose is the following: is that if you take a certain derivative in x variable, let's say beta times, and you take the alpha derivatives in c variable, and this is bounded by a constant. Sorry, I'm missing a constant here. Times 1 plus c to a certain power m plus alpha. So m is corresponding to the order of the operator, and every time you take a c derivative, and in this case, the order goes down by 1. Okay. Now, what essentially this condition says that is that the function amplitude, the amplitude function itself is quite smooth in x, and also has some kind of homogeneous kind of property, at least for large c values. Now, the pseudo-differential operator is very common in scientific computing. And essentially, most of the work that related to linear PDEs has something to do with the pseudo-differential operator. So for example, here I'm giving you this probably one of the simplest elliptic operators. So you have some coefficient omega, and then this is elliptic operating in divergence form. You take the divergence, multiply by omega, and then, take the gradient, multiply omega, and take the divergence. I put this 1 in order to avoid the 0 eigenvalues. So this is a strictly positive definite operator. And you can try to just try to see what is the impact of this operator on f. And after some, like maybe maybe 2 or 3 minutes calculation, you will see that this is actually its symbol. So the symbol involves the omega c, different powers of c, and also the gradient of omega. So for example, if omega itself is a smooth function, and this whole thing is also smooth in x, and also has different polynomial growth in the c variable. Okay. Now, so as I said, I mean, most of the elliptic linear PDE theory and a parabolic linear PDE theory is essentially is about the pseudo-differential operators, and one exception is the linear wave equations. And for wave equations like Schrodinger equations, the more relevant operator is called Fourier integral operators. But these operators also kind of like based on the pseudo-differential operators. Now, why the pseudo-differential operators are good? The reason is that in some sense it's a closed class. This is kind of like for example, if you take, for example, things like inverse for at least positive definite pseudo-differential operators, and also take the square root and many other functions, f smooth function applied to the operator, right? So if this is the operator, you apply a function to it by using eigenexpansion, for example, this is also an operator. So all these operators, most of them, in many cases, can be represented by pseudo-differential operator as well. So in some sense, this is a closed class. So if you apply certain operations, you stay in this class. That's why it's very powerful. Now, we are trying to do computation with the pseudo-differential operator. So therefore, we have to explain a little bit about the computation setup. So we assume that working in d-dimensional space. So in most of PDE theory, D is 2 and 3. But if you work with high-dimensional PDEs, which come from things like molecular dynamics or control theory, finance, and this D will pretty much be much higher. Okay. To simplify the discussion, we assume that the x variable stay in this domain 0, 1 to the power d, and so this is the unit cube, and we assume the periodic boundary condition. Now, in this case, the pseudo-differential operator, the dual variable of x, in fact, is not the whole real line, or the whole real space. It's actually the integer lattice. Therefore, the pseudo-differential operator takes a slightly different form. The only difference is that instead of doing integral in c, you do the sum in c. Okay, the rest is the same. We also assume that the number of points per dimension we use is denoted by lowercase p is actually equal to capital P base 2. Okay. Now, this is still a continuous object, so it's very hard to put on any hardware. So therefore, what you need to do is that you also need to do a little bit discretization. So after doing this discretization at every point, so what you have is that you have this form, the discrete form of the pseudo-differential operator, and you see that the only difference is that instead of evaluating anywhere for x in the unit cube, what we do is that we evaluate on a certain lattice. Okay. So our goal here is try to do a block encoding of the pseudo-differential operator with a certain number of qubits. And the number of qubits we're going to use is d times p. So this, because on every dimension we have capital P points, so therefore we need p qubits to represent the grid discretization in each dimension. And we have d different dimensions, so therefore its natural number is d and p, d times p, plus some ancillary qubits. And here what we're going to do is that we're going to use this standard binary expansion for this x and c, because both x and c are, if assuming p is a capital 2 to the power 2, and so this perfectly represented by a binary expansion. Now, so what related to what I have on the previous slides is that once, for example, you have the block encoding of the pseudo-differential operator, by using these recent developments, which you have heard many times, quantum eigenvalue transformation, quantum singular value transformation, you can actually represent many operators, A inverse square root of A, Fa, using this this block encoding. So in fact, in some of them, you can construct a symbol first and then represent it, but this is also an alternative. Now, regarding the block encoding for operators, which related to maybe partial differential equations, there's this work on block encoding for, sorry, not parse, but sparse operators. This is by this paper by Gillian et al. From 2019, and also this more recent paper by Campos et al. In 2022. And so here they assume that you have some sparse matrix, you have some oracles for the locations of the sparsity pattern and also for the amplitude, and they construct the circuits to represent these operators in the block encoding. And there's also a paper appeared last year that working with hierarchical matrices, and which is sort of in the same realm. Okay, so the discussion of this part I separate into 3 pieces. I will start from the most general case, and then I will go to a slightly more special case, which is I call it separable. So the reason by separable is essentially what you should think about is that you should think about AX C to be a huge matrix where rows are indexed by X and columns indexed by C. And what this formula essentially says that this AX C has a low rank decomposition, where the different modes of the decomposition is indexed by J. Okay, J from 1 to a certain not too large number, maybe 10, 20, 100 or something, okay? And this is the separable case. Now, because we are working with d-dimensional objects, we, in many cases, in fact, you can do something slightly better, which is called a fully separable case. So fully separable means that not only this, you can decouple from alpha and beta, you can in fact decouple from different modes in alpha and different modes in beta. So in some sense, the alpha jx itself can be written as a product of functions which only depends only in one single dimension. Now, the number of terms here might be bigger. I mean, in fact, significantly bigger than here. But in many applications, the number of terms here can still be bounded polynomially in D and also polynomially in low P. Okay. So I'll start from the most general case, and discussion will become more and more explicit, and what depends on more among this structure. So first in the generic case, so here's a circuit, which is in fact quite compact. So the circuit itself, what it takes in is that you're going to take the representation for the function f, and then this Hadamard applied to the all zero quantum state will just spread everything into different modes. And then what we do is that, so here come out is that is really a quantum state which indexed by different QPEs. Now this object here is called a phase multiplier. What it does is essentially multiply the basis x and c and do a rotation and make it become e to the 2 pi I x c over p. Okay, so this is kind of like a phase rotation. And in next slide I will give more concrete slides structure about how this is implemented, but I think the experts know about this. And once you have that, in fact after this step you have e to the I x c multiply f hat c and x, you have it ready. So the next step is multiply this a x c. So this check here is because, I mean, we have to do a little bit different permutation to do the binary encoding, but essentially at this level you can think about this as just a itself. Now, this object itself is called amplitude multiplier, and what it does is really do the multiplication with this amplitude function, AXC. And afterwards you do another a bunch of Hadamard gates and you do the measurement. And on these qubits, which you observe is a result of your pseudo-differential operator. Now, the amplitude multiplier at this point is done by using arithmetic circuits. So it depends on your taste. Some people will say it's quite explicit, but for me, I mean, we would like to be more explicit. So this is one thing that we are not, we will try to improve. So the second thing with this generic case is that, in fact, actually the main issue is that the success probability is, in fact, exponentially small. Because of you double the number of qubits, which you will see that the amount of energy you have in the first, after you do the measurement you have here is actually exponentially small. In fact, it's to the power minus PD. So therefore, this is not something that we, in fact, this is proportional to the number of total degree of freedom in the original PDE. So it's not something that is acceptable. Okay, to fix this low probability, okay, so this is the phase multiplier, and here's the explicit construction of the circuits. What you see is that depends on the binary expansion of your x variable and c variable, you do a bunch of the control rotations, and if you do all of them together, and this will give you the desired rotation that you want. So this is very similar to what happened in for example, in quantum Fourier transform. Okay, the next is the so-called separable case. So again, let me remind you, separable means that this, if you view it, yes?
In the generic case, you view that as LCU, and
a generic case is that not LCU.
So what's the source that of this QPE?
Oh, because we have this PD qubits that will represent this X, right? We actually double it. We introduce another set of qubits to represent Kasi. So in fact, this is X, this is Kasi. After you pass this is X, this is Kasi. So therefore, the number of qubits has actually increased by a factor of 2.
And when you measure,
when you do measurement, you just take the ones that is all 0.
Yeah.
And
so that's the part that contributes.
That's the part that contributes to the small probability. Oh, the B is some ancillary qubits. Because in doing this amplitude multiplier, it needs some ancillary qubits, which I didn't get into in the top.
You need to measure those B?
Yeah, because we need to measure this, because we're adding the Kasi here.
The second measurement. So it's not just a...
Just for the arithmetic circuit.
Just for the arithmetic circuit.
Oh, it's a small block encoding.
Yeah, this is a small block encode. You can erase the last line if you want.
You have some work register to implement that. That's you need to compute to
So, Lexing, can you think of it as this is an LCU, but the one norm of your coefficients is very, very small?
Yes.
Because you treated all terms kind of
Yes,
uniformly.
exactly. Yeah. Okay.
The one norm is very large, right?
Yeah, you can. The amount you care about in the whole energy is very small. Okay. Now, okay. So let's talk about the separable case. So the separable case, as I said, is that you can think about this as a low-rank decomposition. You write this AXKC as a sum of alpha j's and beta j's. So now, eventually, we're going to use LCU to add them together. But so therefore, let's just focus on one term. Let's drop the J index, focus on one single alpha beta pair. Okay. Now, if you think about this, if the symbol itself is just alpha times beta, AXC is alpha x times beta C, then this contribution to the whole thing is, in fact, is given by this formula. Here, all I've done is that replace AXC with alpha C times beta JC. Now you see that this is actually extremely useful, because this is, in fact, the key idea behind all the classical algorithm for speed up pseudo differential operator calculation is that now what you do is that you do the Kasi multiplication first. Once you do the Kasi multiplication, you see that this AX computation, I can delay it, because it's only dependent on X. But rather, this itself has become a Fourier transform. So what you do is that you do Kasi multiplication, you do a Fourier transform to bring it back to the X variable, and then you multiply alpha. Okay? So this is the circuit that's actually implementing it. And then now you see that in order to do this amplitude multiplier, not for the A anymore, but for alpha and beta, we need two sets of ancillary qubits, which is B1, B2, but they are small. You can ignore them for the time being. But essentially, the pipeline is the following, is that you give me the representation of the F. I do a quantum Fourier transform to get its representation in Kasi, this F hat Kasi and times Kasi basis vector. And then you do the phase multiplication on the Kasi variable. Once you do that, you do the Fourier transform to bring this back to the X variable, and then do the phase amplitude multiplication of alpha in the X variable, and then this gives you the result. Okay. So essentially, it's a very simple, it's a rewrite of what people have done in the classical theory in this quantum circuit. And the two things has changed is that classical Fourier transform have been replaced with quantum Fourier transform, and also you need some kind of like oracle arithmetic to implement this phase multiplier. No, sorry, not phase, amplitude multiplier. Okay, so again, I have this front face here is meaning that we want to be more explicit. So therefore, we want to try to get rid of this arithmetic secret.
Yeah. So one question. So here, so in the end, you still need to do the measurement, but you can guarantee the success probability.
Yeah, you don't need to. These measurements are only for arithmetic sequence multiplier for these amplitude multipliers. So it's because you see that previously the problem is coming from this big PD. I'm duplicating another set of qubits to make it work, right? But this is totally gone in the next slide. Now, finally, let's talk about the fully separable case. So again, let me remind you, fully separable meaning that this alpha jx itself can be represented as a bunch of functions where each slot only depends on one single dimension. So this is alpha j1 x1 to the alpha jd xd. Now here, the first index j is corresponding to which mode I have in the original low-rank decomposition, and the second index 1 to d is corresponding to which dimension it refers to. Again, we're going to use LCU to do the whole thing, so therefore, we can just drop the j index and consider each of the alpha x and beta pair. Now, here the circuit only needs one modification, is that instead of doing, because now these are fully separable, right? So therefore, instead of doing this amplitude multiplication all together for all the different dimensions, I can do it multiply dimension by dimension. Okay? So therefore, this means that the tensor product of u beta k and tensor product of u alpha k, and you do the multiplying each dimension. Now, the question next is how do you implement this u alpha k and u beta k, which for every dimension? Well, how do you implement?
How does the number of j affect the complexity?
The j itself is the rank of this low-rank decomposition of this pseudo-differential, the symbol of the pseudo-differential operator.
What if it's full rank?
Most of the good examples are not full rank. Okay, you can certainly construct a full rank example. If you give me a Gaussian random matrix, yes, it's full rank. But most of the scientific computing, this is not the case. Okay. For example, the example I gave you earlier, like for example, you can see that the rank itself is just d plus 1 or d plus 2, I believe. Okay, and even you do the fully separable, you have to make certain assumption on the omega. But if you make a reasonable assumption on omega, this will become fully separable, and the rank itself also polynomially controlled by d. Okay. Good question. Thank you. Okay, now how do you implement this alpha k and beta k? Well, in fact, yesterday there was talk by Mario. Is touched on exactly the same topic. Is that we need to do the multiplication of this alpha kx and beta kc, and let's just call it g function. Okay, I don't care about whether that's kc variable. Now, the idea is to write the g as a function, a different function of the sine cx. Okay. Now x is between 0 and 1, so by choosing c to be, let's say, in a half or maybe a quarter, and any function g can be written as a function for h. Okay. Now, why do we want to do that? The reason is that the sine function itself is much easier to implement with the control rotations. So for example, if you give me a binary representation for x and encode them as a quantum vector, and then this essentially can be implemented by a bunch of the phase rotations, where you just use a binary expansion of the c to do the control rotation. Okay? So this is a related work which was appeared in yesterday's presentations. Okay. Now, once this has become your formula, it's clear that what h should be, right? H should just be take the arc sine of y and divide by c, and then apply g, and this is the function you're looking for. Now, how do we implement this h? Well, again, using quantum eigenvalue transformation and quantum signal processing, and then you can try to represent it with the polynomials, and then you just put in this framework, and you'll be able to have a pretty good approximation for this h. And once you have this circuit, and this is explicit, it does not use any kind of oracles, right? And this can be plugged back into the previous slide into these two big boxes, and this gives you a completely explicit circuit for implementing pseudo-differential operators. Okay.
So when you say sin x is easy to implement, what do you mean? Like a multiplicative operator?
Yeah, sin x is that what you want to do is that you want to implement e to the 2 pi I cx, okay? So you want to take the x and you turn into here. And then, so what you can do is that you can do the binary expansion of the c and then x. So for example, you get c0 x0 plus c1, no, sorry, c0 plus c 1 times 2 to the minus 1 plus da 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 da, right? And then you do x0. Yeah, then you just expand on all of them. And for each of them, you do control rotation.
Then take a real part.
Yeah, then take the real part. Yeah. Okay. All right. So this is the first part of the presentation.
So what
Yeah.
is the L1 norm after doing LCU? I mean, the subnormalization factor.
The subnormalization factor depends on how good the low-rank decomposition you constructed. Yeah, this is problem dependent. Proportion to the rank and also proportional to how good the basis function that the alpha and beta you construct. Good mean that you don't want a function which has a big contrast in terms of amplitude.
Worst case, J could be as large as 2 to the P, something like
Yeah, in the worst case, J could be as large as 2 to the power PD, because if you have a random matrix, you can also write it in terms of the pseudo differential operator, and all the eigenmodes are important.
But this is more efficient than the previous one.
Yeah, this is more efficient when, right? And this happens when you work with PDE problems, and also the coefficient of the PDE are actually smooth. Yes.
Can I ask a question? I was watching online
Sure, yeah.
here. So,
okay.
If you take the function f is e to the TA, right?
E to the
in
T.
your original approach, then you get somehow.
Sorry, f is a function of.
Yeah, or ft of a is just.
Sorry, what do you?
TA.
Fa is e to the Ta.
Right.
Yes.
So then, and then you want to measure the process after some time evolved.
Yeah.
And you have an explicit measurement. Can you get more efficient diagrams and circuits for a specific measurement at time t, right? Because you would measure all the x's together, and then your superposition in x would be simpler. So what I'm suggesting is to incorporate the measurement in x into the picture.
Yeah, we haven't thought about that, maybe.
Because then the superposition over the axis would, you have a problem with your success probability, when I understood correctly.
Oh, I see. Okay, so you're saying that
some advantage of adding the measurement to the implementation.
I see, got it. Yeah, good point. So what you're referring to is that if your measurement operator itself also had this kind of like separable low-rank decomposition, then you can combine them together. Yes. Yeah. Yeah, good point. Thank you. Oh, okay. Okay, yeah, sorry. Oh, yeah, okay.
So I guess I didn't fully understand, I guess, what's the difference between if I just have a block encoding of A versus a block encoding of the pseudo-differential operator of A, and I do this sort of eigenvalue transformation to implement functions of it?
This is constructing the block encoding, but how do you get a block encoding of the original A?
Yeah, I guess, typically.
So we are doing that part in some sense.
I see.
Yeah, in some sense, we're doing the block encoding for A, but through this pseudo-differential operator representation. That may be a better way to market this project.
As a follow-up,
Yeah.
is it possible to show that this is like more efficient than some alternative methods for doing this?
I mean, we didn't do a, numerical comparison, but the alternative is you have to represent with, for example, finite difference, for example. Finite difference is that the main thing is that if you have you need to construct the oracles. I'm not an expert in doing that. Maybe other people can do it more efficiently than I do. And the other thing, my overall understanding is that if you really want to represent PDEs, this is much more accurate because pseudo-differential operator really, in some sense, using Fourier basis expansion. So it's exponentially small error. But once you start doing finite difference, you already have order h square error. And in some sense, sparsity is not super important for PDE problems if you're already willing to do quantum. Because really you're measuring things by log, right? If you're a full matrix, you have log capital N square, and you sparse matrix, you have log capital N, so you differ by a factor of 2. So if you really care about high accuracy, like some people do, then maybe doing pseudo-differential operator is a better approach.
Maybe a counter-argument, potential counter-argument from the quantum community is that if you do it in first quantization, even if you use very large number of grid points, the cost will be log anyway. So it's more about which one is easier to implement. Does that make sense? So even if finite difference use a large number of grid points, but it's not necessarily an issue per se. It's similar to tensor when you do this QTT. I mean, it's the same argument.
But I don't know. But then how many? But there's one is exponential convergent, right? The other is polynomial. So if you take the log, you still have a pretty significant difference if you want to achieve the same accuracy.
There is a difference between log and log, yes.
Suppose you want to epsilon. I mean.
Yeah, I mean you epsilon thing.
You want epsilon accuracy, then the number of grid points you need P is like 1 over epsilon.
Right, but the cost, hopefully the cost is log to log.
Yeah, the cost is log to this.
Yeah.
So it's log P, so it's log 1 over epsilon.
Yeah, and if the number of grid points is already log 1 over epsilon, it becomes log 1 over epsilon, which is good.
So sorry, what do you mean log?
Right.
Well, in the spectrum, you need log 1 of epsilon grid points, and then it's log.
Yes. Yeah. If you already only need log 1 over epsilon.
So the spectrum you say is this. But
yeah. Then you get So you get the log over log, which is good.
If you talk to certain people in scientific computing, they were like 10 to the power 16 digits of accuracy. So.
Oh yeah.
So for this, 1 over epsilon, log 1 over epsilon is big difference.
That's right. Yeah. But I think maybe I mean it's not it's not only for here. I think in other communities like QTT, it's a similar argument. So I mean it would be like interesting, like for example, to see actually this one, for example, is easier to construct, which is also very appealing.
Yeah, I think the point is that we really want to avoid Oracle because Oracle depends on someone else's implementation. Here we just say we do everything by ourselves. That's the point.
Yeah, when we compare to the standard approach, like discretizing any differential equations reduced to like linear systems over, and we usually need to calculate the condition number. So in your approach, what is the small condition number?
The condition number is depend on, as the Link's question asked earlier, depend on how good your low-rank decomposition is. It has to be studied case by case. Yeah.
As you mentioned that you can do simple calculus, directly invert that as a side of, right? So compare that with by using QSVT after this process. So which one you think would be effective?
If you can analytically compute the symbol, then you should compute the symbol first and then do this. If you cannot, then maybe block encoding. The reason is that computing the symbol of, because the operator itself is huge, right? Because this operator, the AX C, if you think about it like a matrix, it's 2 to the power PD, 2 to the power PD, right? So in certain cases, like some work that I did earlier with Laurent and Monet, that we have ways to compute for certain symbols. We have a way to we have a way to compute the inverse of the symbol of the inverse explicitly. But that's quite rare. So in most of the cases, computing this, so suppose this is the symbol of operator A. But what is the symbol of operator A inverse, right? If you only care about the symptotic behavior, that's easy to get. It's just 1 over AX C, roughly like that. But if you want to get it numerically accurate, it's not so simple.
But there is an inverse formula, right?
It's asymptotic, right?
No, this is recursive.
It's
recursive. It's hard. Write it down on a piece of paper, but so I think it all depends whether you have a good representation of the symbol in the first place.
I think that's the algorithm that Lexing was referring to. That you can numerically calculate it, but it's the formula is there, but it's just complicated numerically.
Yeah, if you ever try to do symbols, it's hard.
But this is exponentially large, right? You want to say that, okay, how are you going to compute this on the classical computer or the quantum computer? If you want to compute it on the classical, then we don't even need to talk about this, right?
Right.
If you want to do it on quantum, that's another project. Or maybe, in some sense, QSP is the way to solve it.
There's still the question if you have even if I give you the symbol, implement the inverse, right? It's still very
that's why I was saying that in certain special cases, you can do it in classical way in a very fairly efficient, in the time which is kind of poly log P. So you can do poly log capital P. So it's a polynomial in lowercase p. This you can do it in classically. That's what I was referring to. But that's only special cases.
Very, very rare cases.
Not for general pseudo-differential operators.
There's another overhead when you solve it with the QSP. For example, if you have Laplacian, then the symbol is C squared.
Yeah.
And when you truncate, and it's a pretty big thing, you have to normalize it. And,
yeah.
But if you look at the inverse, 1 over KC squared is actually
that's okay, also true.
Right?
Yeah.
So maybe direct implementation of the symbol, as you said, if you can, I mean, that's a very, very good thing to do.
Yeah. Yeah, right. Yeah, these are good comments. Okay. So I have about another 15 minutes or 20 minutes or 10 minutes. Okay. So I'll try to, maybe I have to rush through the second part. So the second part is the quantum phase estimation. Well, I can skip some over slides because people have talked a lot about quantum phase estimation, both in the tutorial and also in yesterday. So here our main contribution is not, I mean, we rediscover some algorithm along the way, but I mean, honestly, the contribution is not new algorithm, some new algorithm, but the main contribution is, I would say, is also much more careful analysis. So numerical analysis. So the quantum phase estimation problem is the following: is that so you give me a unitary operator U, and I know that U has a, for example, has one eigenvector phi and also eigenvalue lambda. What you want to do is that given the eigen, in the simpler case, is that given the eigenvector, what you want to do is that you want to estimate the eigenvalue. And here we assume that eigenvalue is between 0 and 1 in order to avoid this periodicity comes in. So the textbook algorithm is this based on quantum Fourier transform. It's a beautiful algorithm. But I guess, I mean, these days the comments is that, oh, it needs a D and stellar qubits, so therefore we want to improve this. Okay. Now, another method which has appeared in several times in this discussion is this Hadamard test. So this Hadamard test is probably the simplest circuit you can imagine, is that you just apply the Hadamard gate and you do a controlled U operation, and then you do another Hadamard, do the measurement, and this will give you information about these, the phase information. Now, so here I'm just going through this calculation that if you feed into the 0, phi quantum state, and then each step it would, this writing down what happens after each step. So at the end, I mean, to save time, let me skip this. But at the end is that the state here is just one, is a combination of the 0, phi plus u phi and 1, phi minus u phi. Now if you do measurement, it collapses into this phi plus u phi state, and it collapses with this probability is a 1/4 of phi plus u phi, dot products phi plus u phi, and this is equal to a half of 1 plus real part of phi u phi. So therefore, this part actually contains, the P0 is in fact containing information about the real part of this eigenvalue. Okay. Now, because the measurement itself is noisy, so therefore in order to get epsilon accuracy for this P0, the real part, what you need is at 1 of epsilon square repetitions. Now you can use a slightly different circuits which use the this adjoint of the S gate, and then you will get, instead of the real part, you will get the imaginary part. Okay. Again, in order to get the imaginary part accurately, you need 1 of epsilon square repetitions, and this gives a way to do the estimation of the phase, the lambda. Now, this is a very simple circuit, but again, obviously that 1 over epsilon square, hopefully we can improve this. And in fact, from, for example, Yu's tutorial and also from yesterday, we know that if you do something smart, you can actually get down to something called Heisenberg limit, which is order of 1 over epsilon. Now, the first algorithm that achieved this 1 over 1 over epsilon is probably the Kitaev's algorithm, but this is kind of like give you an illustration about what the Kitaev's algorithm does. Is that assuming that the eigenvalue itself has a binary expansion with d-bit binary expansion, what you do is that you're essentially trying to discover these bits one by one. Okay, there are different versions of Kitaev algorithm, but essentially what you want to do is that you want to use different high powers of u to figure out the corresponding bit. For example, you do the u to the power 1 will sort of allow you to discover the first bit, and if you do u to the power 2j will sort of allow you to discover the jth bit. And if you do that, eventually this will allow you to discover all the bits. Now you can calculate how many bits you need. So suppose the accuracy you need is epsilon. So therefore the number of bits you need, d, is in fact is log base 2 1 over epsilon. And you need to run u all the way to 2 to the power j. So therefore, if you take exponential of this 2 to the power d, it gives you back 1 over epsilon. This in fact gives you these Heisenberg limit, which is very nice. And also it requires only 1 ancillary qubits. So now, here we assume that the phi itself is perfect, but what if phi is not an eigenstate? Okay, which has only some overlap. Now, so this is the this is the general setup. So that you're not providing with the eigenstate with a perfect overlap. Here you only align with the eigenstate that you want to capture with an amplitude of C0, where C0 is something strictly less than 1. And this expansion essentially said that you have some energy in the rest of the modes. Okay. Now, when you apply the Hadamard test, what you're getting expectation is this quantity. It's in fact is a C0 squared times e to the 2 pi lambda 0. This is the part which I care about. And the rest is something that's which we call residual, which is something that actually pollute the system. Now, the terminology is that this C0 squared, oh, actually, sorry, there's no this e to 2 pi I here. Oh, okay, it has to e to pi. This overlap itself is P0 is C0 square modulus square times e to the 2 pi 0. This is called overlap. So in the ideal case, overlap itself has modulus equal to 1. Otherwise, it does not. So therefore, I should put a modulus here, okay? So the rest part is the energy is in this 1 minus P0. Now, in fact, there is an algorithm which achieves what we want, is that to work with this non-perfect input data. And this is the algorithm developed by Kimmel and al. In 2015. And about a couple of years ago, there's the refinement version of the algorithm, essentially the same algorithm. Now, our contribution here is an improved analysis for this robust phase estimation algorithm. And what we see, what we get is that, in fact, you can achieve the Heisenberg limit with an input vector, which actually have only relatively small overlap. In fact, the overlap need only to be 0.5 something. Okay. Now, so there's a lot of work on phase estimation. For example, in the tutorial workshop, Tom has a very nice 2 talks about this content. And also, our work itself, our analysis, in some sense, is motivated by the recent work by Ding and Lin, where they use an optimization approach to do the phase estimation. Okay. Now, the idea is that of the robust phase estimation that it's essentially similar to Kitaev algorithm, but instead of trying to expand things by bit by bit, you don't really need to respect this bit expansion of lambda, right? Because at the end, you only need a real number. So therefore, you can do any kind of like the bisection. So the idea is to build a shrinking confidence interval. So this concept has already appeared in the tutorial talk. So what we show is that, in fact, the initial overlap, the modulus of initial overlap, only need to be bigger than 4 minus 2 square root of 3. And what is 4 minus square root of 3? Well, square root of 3 is roughly like 1.73. So 2 square root of 3 is 3.46. So 4 minus 2 square root of 3 is roughly equal to 0.54.
You are showing your mathematician.
At an elementary school level, right? So where does this magic number come from? Well, the magic number comes from the fact that the following diagram. So suppose that this is the P0. Okay, this is where, I mean, if I measure only the part which is aligned with phi 0, where I'm going to get. This is P0. Now, 1 minus P0 is a residual part, right? So therefore, 1 minus P0 is 1 minus the length of this P. So it's going to, well, I mean, you have no control where it goes to because we don't assume any statistical model on the error or on the input data. So therefore, it could be anywhere in this disk. Okay, here I add a little bit of measurement noise because when you measure, you also have to do repetition several times measurement. But as I will show you that here, you don't need to make the measurement noise go all the way down to 1 over epsilon. It only needs to go down to like a constant number. So therefore, essentially, you can think about how big this disk itself tells you where we can land after we do the measurement. Now, so the essential thing is that you want to make sure that the angle you span here is at most 2 pi over 3. Why is 2 pi over 3? This will come up in the next slide. But assuming you're willing to accept that, and then you can ask is how small can P0 be, right? Well, you will see that if P0 is equal to 4 minus 2 square root of 3, 1 minus P0 plus measurement noise can at most be 2 square root of 3 minus 3, okay? Now, in fact, the ratio between here and here is 2 over square root of 3. So therefore, this angle is 60 degrees. So therefore, the whole angle itself is 2 pi over 3. So this is how much deviation, how much error you can get by using this Hadamard test. Okay, so this is the initial confidence interval. So this is what I'm saying here. The initial confidence interval has to be 2 pi over 3.
Lexing, just understand.
Right.
So this disk is the potential locations of your estimate of
Exactly.
P naught times a phase.
P naught times P naught self is P naught, yes, yeah. My notation is a little bit screwed up because here P naught contains the phase.
Yeah.
Sorry. So therefore, this should be 1 minus absolute value of P naught.
And then what's the radius of this?
The radius is P naught, absolute value of P naught. So think about P naught as a complex number.
So your estimate in principle could lie outside of this.
No, it cannot. It can't. Because P naught is, C0 square times e to the 2 pi I lambda 0. So P naught itself is already a complex number. So that's why I didn't draw down real lines. It has a certain angle here. So this should be absolute value of P naught, sorry. Oh, no, sorry, this is P naught, but the length of this is absolute P naught. So let me, yeah, okay. So the true diagram is this is P naught. This is 1 minus absolute value of P naught plus error, measurement error.
Okay. The origin is
the origin is here. The origin is the bottom left corner. Okay. Yeah, absolute value missing. This screw up a lot of things. Okay. Anyway, so now we have a confidence of interval of 2 pi over 3. Then what do? Well, the idea is to shrink the confidence interval. Now, in order to shrink the confidence interval, that instead of running the Hartman test for U, you run it for U squared. Now, this will estimate instead of lambda 0. So sorry. It should be. Did I change my lambda to, theta. So lambda, I apologize. So I think in the paper somewhere I got switched. But yeah, lambda is the theta now. So instead of estimating the eigenvalue itself, you're estimating 2 times the eigenvalue. Now you're estimating 2 times the eigenvalue with the same confidence interval, right? Because it's the same Hadamard circuit, right? Now, so therefore, if you 2 sigma theta 0 has a confidence interval 2 pi over 3, then what is the confidence interval for theta 0? It's half of this. It's just pi over 3. That's good news. But there's also bad news. It's because everything is periodic on the unit circle. So therefore, if you divide by 2, you get 2 theta 0 correct. But if you divide by 2, you actually have 2 preimages. One is theta 0, the other is theta 0 plus pi, right? So this picture tries to show that. So this is my initial confidence interval. So if I run it for U square, for the Hadamard test, you actually have 2 subintervals. Each have the pi over 3. Now, which one? There's one real one, and there's another one is a ghost one. How do you discard the ghost one? Well, this is where 2 pi over 3 comes in. Because the gap between these two, the real one and the ghost one, is actually 2 pi over 3. So therefore, only one of these 2 subintervals will overlap the interval that I have on the previous stage. That's the important part, right? So therefore, with this information, I can just select the right one and discard the bad one. Now, you repeat this process, and every stage, you can only keep one good confidence interval. The rest of them will not overlap with the previous stages, and you can just safely throw them away. Okay. So this algorithm repeats with log 1 over epsilon stages, and the max circuit depth is O1 over epsilon, and the total cost is O1 over epsilon. Okay. So this is, yes. So I'll go quickly. Now, what do we have a good initial state? Okay. If you have a good initial state, P0 is close to 1, you see the initial angle could be small, so therefore you can actually speed up the calculation instead of you can shrink the prefactor. And I think that Zhiyan will also talk about their approach, which gives the same prefactor later today. Okay, what about multiple phases? Okay, so instead of, can I have 2 or 3 more minutes? Is that okay? Okay, I had a lot of questions. Okay. So instead of having an eigenvector which has only one dominant mode, what if eigenvector have several dominant modes? So we index them by from lowercase s from 1 all the way to capital S. So can we try to estimate all these eigenvalues simultaneously, lambda s simultaneously? Now we have to make certain assumptions. So we assume that if you care about all the modes that we care about, C1 to Cs, we assume that the modulus of them square is greater than a constant called beta. So beta is the minimum amount of energy of the mode that I care about. It has to be greater than omega, which defined to be the rest of the energy. Okay? So because if you don't have this condition, then it's not clear, a priori, what you want to discover. It could be that the residual have more energy than one of the one that you want to discover. Then this obviously is not possible. Now the question is that can we discover lambda 1 all the way to lambda s altogether? Well, the answer is there's already been some work in the literature. So I think the first paper is this one, O'Brien, Tara, Shinki, and also Tahal. And Soma has a paper appeared the same year. So I believe that these papers these are pioneering papers, but they don't reach Heisenberg limit. The first paper that reached the Heisenberg limit is this paper by Dawkowicz, I apologize for the pronunciation, and Tahar and also O'Brien. And this paper does reach the Heisenberg limit, but the dependence on S, the number of modes, is actually pretty large, and it did not discuss what happens when you have the residual. So in our case, we propose a new algorithm, or modification of the algorithm, such that we have a better S dependence. We achieve the Heisenberg limit, and it also allows relatively large residuals. So the residual can go all the way to as big, as long as you're smaller than beta, it's okay. Now, again, our work is related to the work by Ding and Lin, which I believe Zhiyan is also going to talk about later today. Now, the idea is very simple. The idea is that if you take a look at what Hadamard test to give you, the Hadamard test to give you is actually these CS squared times e to the 2 pi lambda s plus some residual. Now, so in fact, what it does is that if you take a look at this quantity, what is this quantity? This is, in fact, the first mode of the Fourier transform of this function, fx, which defined by putting a bunch of deltas at lambda s with weights given by CS modulo square, plus some kind of residual, which we don't know about. So it's kind of, you can think about this to be adversarial noise. Now, in the case of one single eigenvalue, right, in order to get the initial confidence interval for the first eigenvalue, what we need to do is that we need to run this Hadamard circuit with U. Now, for the multiple eigenvalues, running just for U is not enough because it only gives us one number, even for the initial confidence interval. We need to run U to the power k, where k is roughly about an order of s squared, okay, at the stage 1. So therefore, what we get is that we get the Fourier transform of this function, not only at k equal to 1, but at f hat k at k from 1 all the way to s squared. And the problem becomes, how do we estimate this from this Fourier transform, how do we estimate the support? Now, this is a really well-defined problem in signal processing. This is called line spectral estimation, and there's a huge literature on that. I want to point out that the main difficulty here is that in most of the literature, what people care about is the problem where you have some kind of gap between these eigenvalues. But in the quantum case, you have so many eigenvalues because the matrix itself is exponentially large, right? So therefore, the gap itself could be very, very tiny. So therefore, it's important to develop an algorithm which without any gap assumptions. So for that, we develop a new line spectral estimation problem that estimates lambda 1 to lambda s, so that the guarantee, it does not require any gap assumption. It allows pretty large residual all the way to the level beta, and it provides the initial confidence interval of its order. It's 1 over s squared times log 1 over beta minus omega. So therefore, as long as beta over bigger than omega, this is log, this is a pretty small number, and by choosing the constant, you can kill this one. Okay. Now, the rest of the algorithm works similarly. So at every stage j, we're going to try to discard these, we're going to refine the confidence interval and discard these ghost subintervals. And instead of running just u to the power 2 to the power j, we have to run it for different 2 to the power j times k. Okay. And now the algorithm essentially is the same idea. Now here we have the 3 eigenvalues. Initially, if the eigenvalues are too close to each other, we cannot distinguish them, separate them. So at the beginning, we have 2 confidence intervals. But once you start refining, you will see that once the confidence interval is smaller than the gap, you would automatically split it into multiple confidence intervals. At the end, you see that we discover these 3 confidence intervals for these 3 eigenvalues. Now, I want to skip the detail, but I just want to mention that we work with both real power, where you work with u to the power t. This is very reasonable. For example, u is coming from Hamiltonian simulation. And in this case, instead of doubling, we have to choose this multiplying factor between 2 and 4 randomly to avoid the collision, so that we have this well-separated different segments to avoid these, so that we can kill these ghost intervals. We also work with the integer power case, where u is given as a black box, so therefore we only have integer powers of u. In this case, we have to go to some prime number theory and try to choose appropriate prime to avoid these collisions of so that we can kill the ghost intervals. Now, we work with the gapless case, but for the gap case, suppose you know a priori there's a lambda, which is the gap between the eigenvalues you care about. Instead of using the method we develop, you can actually use the music and also aspirate algorithm in the literature to do this line spectral estimation. So this is the summary. So what we get is that for the gaplet case, we get Heisenberg limit. For the gap case, we get something like omega over beta. So you see that we also have this nice prefactor. When omega is really small, this prefactor is small, meaning that the circuit length itself could also be pretty short. Now, to conclusion, we talk about numerical analysis for quantum computing. I talked about 2 examples. at the end, I'd like to thank you for your attention and also acknowledge the funding agencies, and these are the papers. And I also like to special thanks to Lili and Ji and Ding for many discussion on the second part of the project.